Second one is actually GMM. The assumption of GMM is instead of just fitting one Gaussian model, you can fit maybe multiple. You can have mixture of Gaussian model. So it means like here, when you have like a two cluster, so the perfect thing would be, can I fit, instead of fitting one Gaussian model, can I fit two of them? So they can capture both of them. Is it possible to do that? So that's why, so that's the whole idea maybe about GMM, is like GMM. So it's still, the assumption of GMM is you have multiple normal distribution. Because you can see GMM, you can use GMM for lots of time series. If once someone shared it in the stack, you can use it for time series, for image, for different data set. But I'm just want to say that the assumption of GMM is you have bunch of Gaussian model in your data. And if that assumption is not correct, the GMM won't work.
Are there automatic ways to find the number of components we want to use in GMM? How one would approach this if I can't visualize it?
Yes, is one of the things that we can actually try here. Here, so because I know that beforehand, that okay, the number of components is 2, I was managed to do that. So here I had just 2 Gaussian. One of them will just find this one as a normal. The second one would be anomaly for the first one. And for the second one, it will be the reverse. This is the first one, this is the normal, and this is anomaly. And if I combine them, then I should be able to catch it. And as you said, if I change the number of Gaussian here to make it to be, I don't know, 1 or let's say 5, just to see what will happen. See, then the model tries best to find different part of the data to say that, okay, what is my new? You just try to find 5 different cluster of data. And you can see sometimes you have a cluster just for normal, just for anomaly data. So that was a good question, which means having a good assumption about data, which means even one of things, how many components you have in your data is important, because if that one doesn't align with your data, then you will have a weird model, GMM model fitted on your data, which won't match exactly what you're looking for.
So probably one would use some sort of an elbow method.
Like, yes, so it's like there are different ways that you can maybe find the number of, let's say, cluster of data that you have, or how can you actually play with it. And the other thing is, okay, here it's super obvious that, okay, you can say, I know I have 2 components, but what if I use the other, a bit more complex data set? See, each of them are capturing different part of it. What is the correct one here? Maybe. So how can you find what is the correct way of doing that? So you're saying that, okay, I have 2 moon. If I do that, if you make it to be 2, what will be the result? And you can even play with that right now. You can just use different component and see what will happen. See, one of them are capturing the other half, the other capturing the other half, but still all those points in the middle will be normal. So this technique will find anomaly for you, but they are missing lots of points as well, because they have assumption about your data. And that assumption won't always be true.
Is it related to that it's using like Euclidean distance?
No, but we'll talk about them in the Canyon models.
Do you know how the elbow method would work on this when data is structured in this way?
Could you repeat?
Do you know how the elbow method would function, like if you were to try to figure out the optimal number of clusters? Like, I'm just curious about how it would work on that, if it would
to work.
So I would do something like number of components, then some measure of standard deviation of the fit distributions, combined with the probably number of outliers, and make it a single real value, and then see, because like, intuitionally, once you reach the optimal number of Gaussian components, you don't see like adding one extra distribution into your whole data set won't cover an additional cluster of subset of points. So like if you have, say your data set is sort of bimodal, or there are two components, and then you add one Gaussian distribution, it either doesn't cover many points, like they are classified as outliers, or it has a very large standard deviation. You add the second one, the mean standard deviations of both of them drop, and the number of ignored points or outliers also dropped. But once you add more and more, you don't see this significant improvement.
But then it has to be supervised then, right? Because then you assume that you know who are the anomaly, who are not the anomaly, and then so you're constructing a cost function. That's your measure for the elbow, right? So you're seeing your cost function is decreasing.
I'm just hypothesizing how one could. Probably there are ready-made methods, like in clustering. You have the same problem. How many clusters do you want to do? Right?
Because yes, exactly, and there are lots of techniques, because it's not just a problem here, as you mentioned, even in the clustering, because you said distance between them and there's a thing, but in k-means it's maybe kind of like that, because then you are looking, because even k-means is a distance base, and is try to find some core in the data, and is like circular. So it's like saying that the distance you can see it as a likelihood maybe, and what should be the correct k when you're doing maybe k-means.
Yeah.
So there are lots of techniques there, so you can even use them here as well if you want. So it's not like an independent problem, but it's always like they always say there is no exact correct answer for this question, because there are different ways that you can compute, maybe based on even like for k-means, they're computing distance between the cluster, I don't know, within a cluster, between a cluster, likelihood, or maybe something like elbow. So there are lots of ways that you can compute. But here, if you want to say, how good is my model to find anomaly, and which one will help it, maybe I'm not sure what is the true answer for that. But the thing is, we have to explore them all. And to be able to compute, to map a GMM, for sure you need to kind of have an assumption, and you should be able to find the correct maybe number of components in your data. So here it was a GMM, which is like a famous GMM that people are using, and then you can see for two cluster it was perfect, for one is perfect, but when the structure is a bit different, then GMM might not be the best option. So it can kind of cover it.
Because I think in GMM all works based on standard deviation and mean, but there is not any factor about how points are connected to each other, as we can see in the moon problem. The reason they are in one single group is that they are kind of connected to each other. The points are connected, right?
Yeah.
But you cannot. There is no any way to distinguish that by using mean and the standard deviation.
That's why I feel in GMM to calculate the standard deviation so the distance between every other point, I feel it is using like the standard Euclidean distance to calculate the standard deviation and the one point with like another point, like the mean and stuff, right? So that's why it will show this problem, like similar to the k-means, that it can not solve the problem that k-means see. Because for in GMM, even for calculating the variance between points, it's still using the regular Euclidean distance. That's why it's showing this problem.
Yeah, so to kind of wrap up this thing, the assumption of GMM is the data has been generated by, let's say, multiple Gaussian model. And if that one is not true, GMM won't be able to model your data. Because like it's like the only thing that GMM trying to do is using Gaussian mixture, you want to model your data. And so if the data has not been generated by any kind of Gaussian techniques, then it will make it to be kind of like impossible. But for in math and in computer science, it's like an easy assumption that you just think that the data is Gaussian, but not all the time. And that's why you won't be able to just use GMM for weird cases like that. And once we start using real data, like credit card fraud, or I don't know, some time series data, or some complex data, then you have no idea what's inside, what is the distribution exactly, because it's just real data. It's like a transaction of credit card, let's say. And then we'll see which one of these models are performing and how we can actually use them. But the whole point of statistical modeling for this session would be how they are seeing the data and what would be the best thing to do. I guess I had an exercise that you can just use GMM for different synthetic data, but I guess I kind of did that for you. I just tried that, so you can do it afterward as well. So you're gonna skip this exercise. Going for histogram-based one. Histogram-based one, it doesn't have that much assumption about the data, so there is no average or variance. So you're not saying that the source of data is any kind of Gaussian model. So the only thing that you would want to do is to find the histogram of a data, and then based on the histogram, so then because it's just histogram, if it's normal, it will be like a normal. It will kind of match. So it means you don't need. It will kind of solve the problem of number of components, because if it's a normal like this here, it will be like a normal. But if I change it to be like a 2 cluster, then you will see that there is like a 2 like a normal here, and then the histogram will be like that. So you can just use the histogram. That's why they call these methods like non-parametric. You don't have that much assumption about data. You're just saying that, okay, give me the histogram of a data, frequency of different beans, and then multiply them, and then that will be my likelihood. And I can just use that to be able to find any sort of anomaly without having any kind of assumption about it. Yes, okay. So that's what histogram-based outlier detection is about. That just trying to do that. Let me just show you something here. So that's for normal. I want to do two cluster as well. See, that was a 2 cluster. So you can just easily see that now we have like a 2 peak in your data per dimension. So the funny part would be the 2 moon, which is still, it will be super hard for histogram base as well. So that's a 2 moon for histogram base. Sometimes there's a peak, sometimes there's falling down. So it's like a different distribution based on that. So that will be the histogram base of the model. So to be able to use it and stuff be implemented, here I just decided to use PyOD, which is a library that will give you lots of model. So the whole technique in HBOS, as I said, is just computing the histogram, computing the multiplying the inverse of the frequency, and then coming up with a score. And it means if a point is here and here, because the frequency was too high, well, if you multiply them, we'll have like a higher number. So you can say, okay, the likelihood of that number maybe is high because the frequency of that number was high. But as you can see, the assumption here is all these dimensions are independent from each other. So it will make it to be not good when you have a relation between your dimension, but just by assuming that all these dimensions are independent from each other will make these models super fast. So that's why when they are dealing with lots of like huge data, sometimes they're just using this technique because it's super fast, like a lot faster than all these other techniques. And when we are dealing with those bigger data sets, we'll see that clearly. Okay, any question about histogram-based? Okay.
How do you get that curve from the histogram?
This one? You mean, how did I?
Because you're gonna use like the interpolated value to see whether
Yes. Here, you're talking about that line?
Yeah.
Okay, that line is not important. It
It's
just,
not.
yeah, it just just interpolation of between the value and the bin. The thing that the HBOS is actually used is the value pair point. And because you said that, just remember that, see, here I use number of bins. I said pair dimension, I had 30 bins.
Right.
So if it's infinity, that would be exactly
So
that
there's
number.
nothing else in, like, your bin.
Yes. So then finding the correct bin, number of bins would be important here as well. So it means, like if I just divide it, if I say that, okay, I just have 5 bins here, then the frequency would be a lot different if I say 100. And then what is the best number of bins? Like, because whenever we're talking about, I don't know, continuous number, finding the correct bins will matter a lot. Because even for age, if I just use, I don't know, if I say bins of 5 years, or 2 years, or 1 year, it will change the number and the score that I'm computing, and it will affect the score as well. So maybe finding the bin is a bit, it can be challenging when you're using histogram-based models. But given that see, all these model has its own challenge as well. For Gaussian one, it was like the assumption is Gaussian, and you need to find a good threshold to say what is the good threshold for finding anomaly based on the likelihood. Here is like what should be, here is like a kind of like a 2 threshold. One of them is what should be the number of bins, which you can treat as a hyperparameter of the model. The other one is once you multiply them, what will be again the best threshold of finding it. So you can try and play with that as well, because I want to move fast because the time is going. Here for the normal distribution, we can train a model. I guess this should be part of even your code as well, right? I don't know. Okay. So then you can feed that model, which just will compute that one. And then we'll try to find the outlier. And I guess I should be able to just do that here. And then if I haven't done any visualization, so that was one of the exercises that you can do. You can do visualization as well. I don't know, do you have it or is it empty? I'm not sure if I have. Okay then. So then here the thing is like you can play with different hyperparameter, and then you can see what is the effect of the model. So for histogram-based, if I play with the hyperparameter, I can even say that what is the threshold that I'm looking for. But the thing is, as you can see here, the assumption of the model is like that. Is like is the histogram base. And as you can see, if a point, see this point is not anomaly because is per dimension it computing the histogram. So the point in the middle, for that dimension, the frequency is high. For that dimension as well, so here you can say that the +2 for that one and -2 here is like the frequency here is super high. So the probability of this one to be normal is like the histogram-based model will say that point is actually normal because per dimension there are lots of data that will back this sample. So it won't be able. It will find those boxes or a square per dimension and it will say, okay, that one. That's why I was trying to do that here. Let me make it to be 2 cluster again. See, so per dimension there's a 2 peak, and if anything is in that area or this area, per dimension doesn't matter because they're independent from each other. It will say that's normal, and other than that, it will be that's fraud. So that's why for the normal, anything here will be normal as well. Anything here will be normal as well. Same thing happening here. See, if you're going down, going up, these are like a normal as well. Same thing happening here, and for that one, because there are lots of point, based on if you change the threshold, you will see different things. But again, it will per dimension. It will try to find a box. And then based on that, we'll try to compute the kind of not likelihood, but the probability of maybe having that point to be anomaly because the histogram base.